So I'm Hendrik Wieberg. I'm very pleased to introduce our company Emission C, where the subject is European quality biochar equipment with a return on investment less than 5 years. Forgive me my English and my presentation style. My wife is much better in this, but she knows nothing about biochar or Emission C. Emission C has the knowledge to make biochar from organic waste, and we are already doing tests for a year. We ordered in China in August in 23 a machine that is installed in February of this year. And we had a lot of troubles to operate the machine. So we started to rebuild it, and now we are in the possibility to make good biochar on a safe and good manner. And we know what we have to do for the future machines we want to sell in Europe. Emission C is also, we are completely responsible for the complete design. And in collaboration with our customers, we do the preparation of the financial plan and the feasibility study. So who is Emission C? We are with three persons. So Sam de Schepper, you see first, is the expert in mechanical and piping issues. Previously, he was the owner of Indinox, a company that handles the mechanical side of industrial projects and also for Emission C, as well as innovative companies such as EcoTreasures, Alenco, and Biodiesel Company. He is currently a partner and co-shareholder of Emission C, where he brings the mechanical and chemical knowledge needed for this project. On the other hand, we have Johan Agnesis, who comes from the world of juice processing, with expertise in cultivation of medicinal plants. He serves as commercial manager of Emission C, and thanks to his knowledge of organics and his extensive relationship in the sector, he plays a crucial role in the company's commercial strategy. And myself, I'm former founder and shareholder of HIEK, a company specializing in electrical installations and automation in the broad industry. I'm currently CEO and shareholder of Emission C, and I am a mechanization engineer and responsible for the automation, communication technology, and electrical installations required for our activities. So as I told, we bought an installation that we want to use as demo for potential clients to show how the system works. This was before the installation was with us. And in the meantime, we installed the skid in our workplace in Lokeren. This is in the very beginning, and we did a lot of adaptations to the installation. You see in the following slides. Here you see the one side of the machine, and the other side I give some more explanations with the PNID who follows. The other side, where you can see at the green house and the rest of the installation, we did a lot of insulation. And the IBC is where we put the carbon in when it has been paralyzed. So this is the operation panel where we're working with at this moment. And here you see the screen that we have on an operation panel, where we have here a transport belt, where we put on the organic material into a vessel, where we have a screw who puts the organic waste into the reactor. And the reactor is turning a screw who puts the material into the reactor. It's a double drum reactor with two cylinders, an inner cylinder where the material goes to the right side, and the outer cylinder where the material returns back to the gas chamber or gas lock as you want, where we separate the biochar, goes to this side via the cooling dischargers, 3 cooling dischargers, and an airlock valve into the IBC. The cooling discharges are for the temperature of the biochar may have maximum 80 degrees when it comes into the IBC. On the other hand, we have the gas will be sucked by a cyclone and a manifold by this induced draft form and goes by this side into the furnace where we burn the syngas together with the air that's thrown this way through the heat exchanger into the burning chamber. We start the installation with a gas burner to reach a temperature of about 350 degrees. Then we put in the organic waste, and after about 10 minutes, we have the syngas, and then the system turns on its own. We can put the gas burner out, and the syngas will take over the warming up of the furnace. The reactor is turning with this carbonization host at a speed of from 1 to 10 tours a minute. Further, we have also the outside of the gas, who is through the heat exchangers by this induced fan, and then will be washed into a washing column here and throw into sulfonization tank. For the cooling purposes here, we have a cooling tower with the water who circulates in between this system. Now we use about 50% of the syngas for the process, for the pyrolysis, and the other hand, 50% can be used for other purposes, such as heat or electricity. This is the PNID of our system that we have here in Lokeren. So in the middle you see the reactor with the gas lock, and it's the same as I already explained, only it's in the way of a PNID, where you see the syngases go to the furnace, and the rest of the gases will be burned, and the outlet gases will be washed in the same. This is the principal flow chart of the machine. You see the machine where we put 100 of organic material into our machine, and it splits up in 27% biochar, 3% is wood, vinegar, and tar. And then we have, on the other hand, 70% of gas, where we use the half. We are 60%, with 50% for the burning and for the furnace himself, and the rest can be used for, as in this example, with a boiler to make heat, hot water, or to make electricity. For infeed, I come a little bit further, but we are also busy for soil and cleaning up from PFAS and PFOS with phytoremediation, where we make biochar from the hemp who takes the PFAS and PFOS out of the ground. So from inputs, there's all organic waste can be put in. The importance points of the feedstock are the moisture of less than 15%, and we work in pellets to have a continuous input in the machine. We already turned with our machine at wood pellets, hemp, Texas, then centus, horse manure, sludge, and from wastewater and straw. As you know, there's the output from biochar. You can do a lot of things with that, such as soil remediation, but also in the extreme form, make active carbon of it. But also the wood vinegar and tar in a small amount are valuable. And then the gas is used to do to feed the carbonization furnace and can be used for energy purposes. Here you see the boiler where we burn the syngas to make hot water, and we have the intention to test on organic Rankine cycle, where we need to make clean syngas before we use this machine. So for the carbonization or the biochar, there are a lot of industries who are interested in this. It can be for carbon sequestration and emission reduction, for soil remediation, the reduction of sludge, agriculture and forestry waste recycling, but also for biomass to produce steel or silicon. I show here the mass balance. I won't go in details, but if you want, I can more explain. Anyway, if we put 100 kilogram of biomass into our reactor, we have 28.5. It depends on the temperature and the residence time of the biomass. It's about 30% and 70% will be gas, the syngas, where then the half will be used for the reactor furnace and the other half you can use for other purposes. The energy balance, you can see the kilocalories of the gas that used for the reactor and can use for other purposes, which we have on charcoal and other materials. So we are in speaking terms with the European biochar company, of how I say that. It's they give the guidelines for the production of the biochar, and we aim to realize the carbon credits for our clients. Therefore, we speak with Plus, Puro, and Vera. I won't give details for this because it's not the subject of this meeting. So now I want to explain what we changed or intend to change to the installations in the near future. Because we learned that we cannot change everything on the machine we have bought because of mechanical requirements, but we aim to change it for the next machine. So the 1,000 I will present, the 1,000 kilograms an hour. And these changes, improvements are essential to deliver a safe, workable, and compliant installation for all different governmental issues. So here you see the design of our EMC10. The principle is the same as our demo installation, only we do a lot of changes on the equipment, which I will explain you later. We change also the gas washing, and the materials used are from other types as we have now in our demo plant. So what's the difference between the demo and the EMC10 BC? The material of the reactor is in stainless steel 310S, which makes that we can handle higher temperatures. This means 750 degrees instead of 450. And we also changed the dimensions in function of the capacity and the residence time. Also, we make a heat shield between the reactor, the chain who's turning the drum reactor, and the running wheels. So this is for making the machine possible to work on continuous running. Also, with the ceiling head, we had a lot of problems with this installation here. We changed them to the stainless steel material, the same material, also for the temperature. But the very important is the seal, where we can have a maximum pressure of 2 bar. If we work in under pressure of about 50, 100 millibar. But what we have with this installation here, when we have problems with the ventilator, I say, then we get sometimes overpressure and problems will start. So this won't be possible anymore in the future. And instead of a screw where we put in the feedstock now, we will change it to a direct input. Also, an important point is the outlining of the ceiling head with the reactor, where we can do at our installations anything now, but we will do it in the future, where they can be out in line with each other, so it can be regulated, and with compensators for the temperature and turning proposals. So the burning room, we also changed so that we can have temperatures of 900 degrees, and we put insulation inside, high temperature insulation, about 150 millimeters inside, and the seals will be designed now also for continuous running. On the outside, we have enough free space to make insulation of minimum 200 millimeters to get a maximum outside temperature about 40 degrees. And then also the burner. I go back to the previous slide. You see them here. With the system now, the syngas is blown with air into the furnace. We will change this with syngas burners, who has also a pilot burner and a controlled system to make a better regulation and control. On the side of the syngas, we changed dust filtration with ceramic filters to cyclone instead of cyclone. And we go at higher temperature to make condensation impossible. And so the syngas and tar and vinegar stays in gas form. We have installed a three-way valve to control the temperature of the system. And so, as I told, the syngas burner is with pilot gas instead of burning like now with the oil burner. In option, we also can provide condensation and distillation to have separated tar and wood vinegar. We also changed the transport of solids for the dust filtration. We changed the screws where we had the cooling screws with magnetic couplings and have installed double rotating valves with nitrogen binder at inside to enter the gas lock. And we provide everything to make a maximum heat recovery with insulation and tracing. And heat recovery is used to dry the feedstock if necessary. So we're also busy to do something with the emissions. That's water and gas, the outlet gases. And there we are in speaking terms with companies who will do the analysis of these. So here I'm at our models. We aim to have 4 models. The smallest one, like we have here, is 250 kilograms an hour. I will take my here, so. Then the 10, that's what I'm presenting now, 1,000 kilograms an hour, 3 and 5,000. And each machine can be provided with drying. That means drying of the feedstock with the outlet gases of the machine, the heat of the machine themselves. And then a heat production or electricity or both with the syngas that we have, how you say that, extra. The machine, here you see the footprints of the machines from the 4 types, and the electricity consumption, the diameters of the reactor, the stainless steel that we use for the reactor material, that we work with negative pressure, speeds, and so on. Here there's the feed requirements, size 20 millimeters and less than 15% moisture. So we come to the return on investment, where we have taken our machine, the 10 BC, we can do this for all of our machines, but we take this as example, where you can suppose a selling price of about 1,475,000 euros. We need 1 full-time equivalent per shift. The feedstock is 1,000 kilograms an hour. So we calculated with 50 euros an hour for the labor cost. We're working 3 shifts a day, 5 days a week, 45 weeks a year. And then we have some assumptions. We calculated 80 hours a ton for the feedstock cost, the cost electricity for running the machine at 0.25 euros a kilowatt hour. And then we suppose of SM 350 euros for the revenue on the biochar and 150 euros a ton for the CO2 reduction. Also for energy, we put 25 euros per megawatt ton, and we have a heat production of 500 kilowatt hours. It's in between 1,000 and 2,000, so we put it very low because maybe we can use some. So in the next slides, you see the expenses and the revenue. Here we have the expenses for the raw materials at the 80 euros a ton, the labor cost, the electricity, gas consumption for each startup, you need some gas, and then the depreciation of the equipment at 5 years, and we think you need about 5% to do maintenance at the machine. On the other hand, the revenue, where you can earn 630,000 euros for the biochar, for 1,800 tons of biochar, 4,500 tons CO2 reduction makes 675 CO2 carbon credits. And then you can choose heat, electricity, or both, but it's on what you can earn with that, and it makes 1,372,500. So that makes a difference of about 300,000 euros and gives a return on investment of in less than 5 years. We did analysis of the biochar, and we are glad with the results we have. So these are analysis done at the 3rd of July at 3 different feedstocks, where we get a dry substance of about 79 to 89%, with a small amount of humidity and with a nice pH. So here you see the organic carbon of 84, 83, and then the total carbon is mainly the same because sorry, the I see, forgot what it was, is very less. Sorry, you can just pick up. So I see this is anorganic carbon, this stream. It's less than 0.18%. This was Ilvo who did the analysis for us, and now we have to see with our clients what their needs are for the biochar. These are our contact things where you can find us. So feel free to contact us if you're interested in the machine that we present. And thank you for your attention.
Thank you very much, Hendrik. Thanks for the presentation. Sorry, the floor is open for questions. So you got one question. So, how many modifications and how costly did you have to perform to make the core paralyzer operate well? So your current pellet plant.
We did a lot of changes, so which I described, and the cost of it was about 200,000 euros. So, but that's for the small machine. This will be more important for the big one. We are now looking for European constructors for the drum reactor, but maybe we stay with our Chinese partner to make them. That we are not sure. But we are handling everything out of the drum reactor, which is okay when they make it in the stainless steel as we want to. And the other parts we will build up ourselves.
And
so that means the gas lock, the seals, the rollers to turn on, the fans, and so on. The gas washing, the water cleaning, all these things are we taking into ourselves. But now what we have from the machine is still about 80% of what we got from Weston, the Chinese machine builder.
Okay. So Michael was asking, what are the free certifiers you mentioned for carbon crediting?
We are still handling with this because there are a few systems or different ways to get the carbon credits. And I see that like Puro or Vera or Plus, they have all their own systems. So I think that we have to go in discussions with our potential clients, what they prefer, which way to earn the carbon credit. But we are really, the goal is to have machine certificated to reach them. And certificates are not for us, but are for our clients.
And because you mentioned you had a Beston machine, so do you think they wouldn't get a certification with their original model?
No, not at all. It doesn't answer at the European quality standards, and they are not busy with heat recovery, with outlet gases, with safety, and also the European machine construction guidelines and things like that. So no, it's impossible.
Okay.
The changes has to be done to sell this in Europe.
And you mentioned that you will, so the main drum reactor you might still purchase from them, but the accelerate.
There's
Accelerate.
not direct question. We have also contacts with other mechanical partners to build the reactor. It depends on. And we have now already offers from China, but we still not very comfortable with this. And so we have contacts in other European countries who also have the possibility to build this.
And do you already have an idea about your future customers? So any feedstock you want to focus on, or is a general pyrolysis
Yeah,
system?
but it is important that the feedstock is constant. That means dependent of what the client has from feedstock. If he has his own waste to use as feedstock, but it has to be pelletized, and the moisture has to be less than 15%. And we see difference between one and another, but it's all in a nice way. So that means that once the machine is installed for a certain feedstock, you can go on with it. But you cannot change the one day to another from, for example, Texas to hemp without adaptation. So then you have to change some parameters. But our opinion is that everything has to be in the right figure. That means that you have feedstock at a reasonable price. You can sell your biochar at a reasonable price. You can earn the carbon credits, and you can do something with the energy. And then when these four are aligned, you have the return on investment that will be less than 5 years. For the bigger machines, it's even shorter than this.
Yeah, I really prefer like that you put 350 euros per ton of biochar because I think that's a reasonable price there. So Nikos was asking, is the business plan presented here based on one particular feedstock or multiple ones?
Multiple ones. Now, it's not that important to feedstock. Well, it has to be at the right form and moisture, but also therefore we help our clients and provide the installations to dry, to pelletize, to wash, or whatever is necessary to get it in the right form.
And that was also a question in the chat. First of all, do you include the pelletization in your business case?
Yes, we do everything that's preparation, but also after making the carbon. If you want the carbon in a form, a way, you want powder or you want bricks or whatever. We want to do the complete chain from feedstock till carbon with heat recovery for electricity or boiler substance, heating substance, what I know. Yeah,
And
we do.
and maybe based on that, so why do you need pelletized feedstock in the first place? I mean, I understand it's preferable because it's very homogeneous, but what happens if you use flakes, for example?
Oh no, it works. The flakes is not the problem, and chips neither. It's about when we tried also to put hemp and Texas as such in the machine without pelletizing, and then the pyrolysis is not stable. It gets turning up and down, and you have not a constant quality.
Mhm.
The reason of pelletizing and the handling like that is more for quality reasons of the biochar.
Okay. I had a follow-up question that so you mentioned that your new design will have a direct input without a screw.
Yes,
So it's a gravity-fed
I
hopper.
go back to the slide and you can see that because maybe I go too fast on this, but it's not so easy to show it with this. But you see the infeed here, where the material gets right into the gas lock.
Ah,
And yeah, that's it because the machine we have with us, I show here. Wait, Yeah, you cannot see it here, but here. Huh?
Mm-hmm.
Here, that's how the material is feed into the drum reactor.
Mm-hmm.
And that's not, in our opinion, not the right way. So we will do it on another way to get right there. But with anyway, we have a gas lock with two valves
Mm-hmm.
above and under, and with nitrogen in between.
And I guess if you use a gravity fed system, then you need pellets most likely.
Yeah, that will be the same. That will the pellets is more for uh, constant feed reasons. If
Mm-hmm.
you use others, the measures are elsewhere, and there is a lot of more air in between, and we don't want to have zuurstof, we say that oxygen in the reactor. Pyrolyze is burning without oxygen, right?
Yeah.
Physical.
And then another question from Gonzalo was, what is the ideal size of the feedstock beside pellets, or what's your maximum size you would be able to feed? Do you know?
You can say again, what is
Uh,
the?
Maximum size of the feedstock you could feed if it's not a pellet.
Uh, I I think it depends on the feedstock. If it's wood pellets, I would as such. It can be 5 centimeters at 1 centimeter.
Mm-hmm.
Uh, the point with wood is that it doesn't take that much oxygen with it.
Mm-hmm.
But if you take plants such as hemp or taxus, yeah, you take a lot of more hemp in it, and it's not dense enough to make a stable pyrolysis process.
Okay. Um, Great. I think if I forgot a question in the chat, let me know because there's a discussion about the biochar certificate price. Can you maybe just quickly mention how you came up with, I think you had 150 euros per ton of CO2?
I can show another presentation for that, where there are. Is this possible in this? I try, huh?
Not sure.
Look, biochar.
You might have taken the Pure Earth.
Yeah, maybe I have to do a new. Wait a second. How do I do this? Oops. Good. Yeah, do you hear me?
Yeah,
Okay. Share. Now you will see a beast.
yeah, we see the Highland cow, which I like because I'm in Scotland.
And now I'm taking the presentation there. So, so
Yeah,
I go to the slide about. You see now my slides, eh? Yes.
yeah, yeah.
I hope. Okay. I go further to the situation of the biochar, the carbon credits. It's not very clear for you, I think. Where is it here? Yeah, business model. Try to let it grow. So there's the evolution of the biochar. We are now at 23. The price of biochar, yeah, but we were talking about credits. So here they assume even higher price than what we suppose at 350. And then we have the evolution of the CO2. This is carbon credits,
Mm-hmm.
where there will be expected that they will be ongoing higher the next coming years. And indeed, here is not 150. We calculated with 150.
Yeah, there was just a discussion in the chat, and
Uh,
I think So because we are a bit over time, so I think that's all for now. From from you, Hendrik. Thank you
Yeah.
very much for your presentation, Hendrik.